Hi, welcome everyone. Today I'm going to talk about some simple examples in solving forces behind retaining wall. So design design wall. And this type of problems is very popular in FE exams, civil engineering, fundamental engineering exams, the geotechnical portions. So let's start with the most basic example. Let's see here we have a uniform dry sand as a soil backfill acting on the retaining wall, and we want to find out what is the force that the soil backfill here now is providing to the retaining wall at rest conditions. So we still have the Ka active and Kp passive conditions, but now we just look at the at rest conditions. I will have more tutorials coming up, look at different scenarios and different loading conditions, Ka or Kp, and also like whether they have water, and also if we're looking at second examples we'll look at today, also like the two-layer systems. But let's start with the most basic one. So this is a plain simple soil profile, and please also subscribe to my YouTube channels, and there will be more design examples to help you to take your FE exams in the geotechnical engineering part. So let's start here. I have some recommended procedure for us to solve for the not only the force behind the wall, and also we're talking about the locations. Where is this force acting on when we do our static problems? Some recommended procedure. First, we will find the vertical stress at the base of this retaining system before we find the horizontal stress, because we are talking about the horizontal force acting from the provided by the soil backfill, which we need the K0 value, which is the coefficients, lateral coefficients, like for lateral coefficient pressure, and we are talking about at rest conditions. So that's why we need the K0, and K0 values depends on the soil type. If we have a normally consolidated soil, then the K0 equals 1 minus sine phi, which sine phi, the phi is the friction angles. So this is a uniform soil profile. So the whole profile has the uniform unit weight and also uniform friction angles as the first steps. However, if your soil is overly consolidated, then the K0 values would need to consider the overly consolidated ratios to a power m. So m for typical soil is about 0.4 to 0.5, but you need to check for design which parameters there will suit your soil type. But bear in mind that here now, make it simple. When you have normally consolidated soil, then use 1 minus sine phi. For overly consolidated soils, use 1 minus sine phi times the OCR to power m. And since our materials mostly are granular materials, and most case we for design or for constructing retaining wall, in the most case the soil is normally consolidated. So today examples we will just work on normally consolidated soils too. So after we know the K0, then we can find the horizontal stress. Horizontal stress will be equals to the K values. This case at rest conditions, so it's K0 times the vertical stress. But if you have active conditions or passive conditions, then you will use Ka for active and Kp for passive. And we have more examples when we get to the point like we talk about active versus passive versus K0. So by knowing K0 and also vertical stress, give us the horizontal stress, which is the key for our retaining wall design. So after we have the horizontal stress, so this is an important step. So this is now we can able to do to draw our stress diagram. So stress diagrams is using knowing the horizontal stress and also knowing the height or the geometry of a retaining wall. So the stress diagram pretty much is using the horizontal stress on the X and using the height that you're looking at as a Y. So you have the X and Y. Then we can calculate the area of this green triangle here, representing a stress diagram for this soil profile. So similarly, like now you have a triangle, so it will be 1/2 base, which is the sigma pi h, times the height, which is the vertical dimensions here. So after knowing the P naught, which is the area of the triangles, and we can find the locations where this force acting on is here. Since this is a force diagram, so the centroid of these triangles represent the locations where the force acting on the wall because of the soil profile. So in this case, since we have a triangle, and we know the centroid of a triangle is 1/3 from its base. So for this case, for triangle, so be 1/3 times the height. And if we have a more complicated geometry where we will look at when we get to the 2-layer systems, now it's just 1-layer systems, then at that time, we need to take moment to find the locations of the resultant force overall, and we will work on it when we get on the 2-layer systems today. So this gives you a basic idea on how to find the resulting force and also the locations of it from one simple dry sand profile, given that it is at rest conditions. So again, we're looking at the dry sand and also at rest conditions. So let's work on examples together quickly. Let's say we have a soil profile here, standard uniform unit rates of 19 kilonewton per meter cube, and the whole layers, the whole 10 meters of soil here behind the retaining wall has a friction angle of 35 degrees. So to work on a problem like this, again, what we try to do is we try to solve for what is the resultant force, like P naught here, acting on the wall, and the locations of this resulting force. So first, we calculate the vertical stress at the base of this systems right here. So it is the vertical stress equals to the unit weight of the soil, which is 19 times the height or the elevations that we're looking at. The base, that will be like the bottom 10 meter. So we get the vertical stress, and we know that K naught equals 1 minus sine phi, as we previously mentioned. And this is we assume this is a normally consolidated soil. So for problems given to you, they will tell whether you're normally overly consolidated soils or even giving you the K naught values. Now we assume it is normally consolidated. Then we got a K naught upon 426. So we know the K naught, and be very careful when we use these equations. Horizontal stress equals to K naught times vertical stress. It must be in effective stress base. But so far, since we don't have water, so that's why the total stress is equals to the effective stress. So that's why we are okay to directly to use the 190 that we previously used for we calculate for vertical stress, and then times the K naught. Then we can get the horizontal stress. Again, it only works for effective stress base, but since now we don't have water, then effective stress would be equals to the total stress. So when we find the effective horizontal stress, it will be equals to K naught times the vertical stress, so which is like a 0.426 times 190 for this case. Then we get the horizontal stress equals to 81 kilopascals. And both total and effective stress, they're equal because we don't have water. We're working on dry sand profile. So with that, we are able to find the vertical stress and the horizontal stress. So once we're able to find the horizontal stress, remember we want to plot the stress diagram, and knowing that this triangle will be a triangular shape because the horizontal stress build up through the depth, and we know at the base we calculate the horizontal stress, and that is the base of the stress triangle, and the height will be the given wall dimensions, which we assume are the backfill to the top of the wall, and it become like a basic triangle area calculations. So the resultant force equals to the area of this triangle here, then 1/2 the horizontal stress, which is x dimensions here, and the y is the height. So the triangle of this green triangle is 1/2 horizontal stress times the height. And we do our math here, 1/2 81 kilonewton per meter square times 10 meter. We got 405 kilonewtons per meter. So we're talking about, since this is a 3D problems, but we simplified in the 2D, two-dimensionals on the paper. So the force supposed to be in kilonewtons. So we are talking about kilonewton per meter. So the dimensions is the 1 unit, the unit dimensions is the directions that coming out and go into the page. So coming out from the screen and going to the screen, that is like a 1 meter, so per meter. So kilonewton per meter. So if we know like the other axis dimensions, we multiply that, then that will be your final resultant force. But now we do everything in 2D. So this is the force that we find, and realize that in your FE menu, it provides a formula like this to calculate the resultant force. And actually, this formula, if we substitute the sigma h, the horizontal stress calculations, with K naught times the vertical stress, and vertical stress equals to gamma times the h, then you will become this formula. So when you have a single uniform soil profile, it is okay. If you want to save time, you can directly use this formula here, 1/2 a unit weight of the soils times K naught times h squared. That gives you also the same results as what you go through this, my recommended procedure. You find the area of the stress diagram first, then you calculate the area, then that is the P naught. So it is the same thing, but like this formula you can directly use only if you have a simple soil profile like this. On the next examples, when we see we have 2-layer soils, and later YouTube clip that I will also mention some more examples, when we see there's like an effect of water, then that's a total different story. So we have very different results from there. So this formula again is only work for 1-layer systems. So that's why I recommend you try to develop a habit on trying to like develop like the procedure here is always draw out the stress diagram. Then it helps you to see how to calculate the forces at different soil layers, which we'll cover next. But anyways, like now we find the P naught. What missing information now is the locations. And again, we only have one stress diagram here, which is a triangle. And we know the centroid of a triangle is 1/3 of the height. So if you know the height, we divide by 3. So from the base, 3.33 meters, that is the locations of our resultant force for adding on this retaining wall, given that like we know the unit weights and we know the friction angles of the soil, then we are able to calculate the resultant force. This case is 405 kilonewton per meter, and also the locations where this force is going to. Okay, next I want to talk about go to one more step ahead. So now we are not only having 1-layer systems, but we have 2 layers. Still dry sand at K naught conditions, but now it's get a little bit more complex, but yet is manageable. But the same thing, we want to find the P naught. What is the resulting force acting on our retaining wall, and where's the locations this resulting force acting on. So again, I have some recommended procedure when you see a 2-layers systems on dry soil. First, you will find the horizontal stress at the bottom of each layers. So you find like the horizontal stress at the bottom of the first layer and also you find the horizontal stress at the bottom of the second layers. So find the horizontal stress, but before you get there, you find the vertical stress, right? And also find the K0 values for each layers. Then you're able to find the horizontal stress. We'll work on some one examples problems together. Next, then you will find P1. So since you know this horizontal stress right here, then you also know the vertical dimensions. Then the force of this from this first layer to the upper portions of this retaining wall will be equals to P1. So P1 will be equals to the area of this green triangle again. So once you find out your sigma H1 there, you know the height. So it's 1/2 of the horizontal stress times the height. Then that will be the area of the green triangle, and that will be equals to P1 here. Next, we want to find P2, which is the belongs to what is the first layer soil horizontal loading acting on the lower portions of the wall. So this is P2, which is the yellow rectangles here. And since we're talking about the force on the first layer to the second part, the horizontal stress is not changing from the first layer to the second layer. So since this stress is not changing, it's the same one that you find. So this unchanged, and you know the vertical dimensions. So you have this. So we always know H1 and H2. So 1/2 the horizontal stress times H2, that gives you the area of the yellow rectangles here, which corresponding to the P2. Again, P2 is the force from the first layer to the lower portions of the wall. So similarly, then we want to find P3. So P3 is the pink triangle here, which corresponding to the force come from the bottom layers of soils to the lower portions of your triangle of your retaining wall. So if we able to know the sigma 2 horizontal force from the second layers, calculate from the top of the second layer. So we know this dimensions right here, and then we know the height of H2. So 1/2 the base times the height give you the area of the pink triangle. Then we can find P3, and acting up P1, P2, and P3, the summations of those three resultant force give you the total force, or the overall resultant force that acting on the retaining wall come from the top and the bottom layers of the soil. So last but not least, we find the locations where this P0 form. Since now we no longer have a simple triangle area, we have three areas. We have a triangle with rectangles and another triangle. So if we take moment that like a P1, P2, and P3 acting on to the wall to the resultant force against provided by the wall to resist the soil body loading. If we take this moment, then we can find solve for the locations where this resulting force acting on, counting from the base of the specimens, and we need to take a moment at this point over here. So this particular point of your retaining wall. So let's try a quick examples together. Now we have two layers. We have the upper and lower layers. The upper layer is 6 meters. The lower systems is 4 meters. And the soil properties change. So the unit weight was 19 on top and 23 in the bottoms. The friction angles increase slightly, 35 on top and 37 in the bottoms. So procedure-wise, first we want to find out the vertical stress at the bottom of the first layer. So it is the gamma 1 here times the 6 meters. Then we give us the vertical stress. And we can find the K naught values, which is the 1 minus sine phi. So the phi is 35 degrees on the top. Then we find the K naught values. And we want to find the horizontal stress again at the base of the first layer. So that will be equal to K naught 1 times the vertical stress that we find out. For this case, we have a horizontal stress acting right here at the base of our first layer, which is 48.6 kilopascals. Similarly, we do find the vertical stress at the base of second layers, but bear in mind, when we find this like a vertical stress, we count from the top of the second layer. So that's why the vertical stress is the gamma 2 times 4 meters. It's not like you need to consider the first layer. Now we just look at the force on the second layers to the wall. So this like a sigma 2 is only have a thickness of 4 meters. So we know the vertical stress. Similarly, now we're plugging the friction angles at the second layers using the formula 1 minus sine phi. Then we can find the K naught 2. So we know vertical stress and we know the K naught. Then we can find the horizontal stress, which is 36.63. And you will wonder why this number is smaller than the sigma 1. So sigma h2 is smaller than sigma h1. It is because, again, the way we calculate sigma h2 is count from the top of the second layer, such that like this case we have a thinner second layers. So no surprise that we got a horizontal stress smaller than the one on top of it. So this dictated by how we draw the stress diagram and we talk about it. So once we find all the horizontal stress and the vertical dimensions is given, then we can find, you can draw the stress diagram. So the first stress diagram is the top layer, and since we only have top layer, so it's a triangle. Whenever like we just talk about single layers, and we treat it as a single layer when we just look at the top. Then it's the green triangle right there. So using the formula one half of base times height. So the base is the horizontal stress that we calculate, which is like a 92, and then times the height, which is 6. So 1/2 92 times 6, we got the P1. So the P1 is right here. So the force that acting on the upper portions of our retaining wall, 6 meter, from soil layer number 1. So that's just P1. And next, then we would do the second component here, which is the rectangle, the yellow rectangle we see there, which is the stress come from the top, or the loading from the top layers to the lower portions of our retaining wall. So P2 will become this rectangle here, and the stress, the horizontal stress wouldn't change because we're talking about the effect on the top to the bottoms, and the end of the top start here. So to the bottom, still maintain the same horizontal stress. Again, it's from the top layer to the lower layers. So this case, for this rectangle, so the width is the horizontal stress, and the length is the height of this wall. So P2 will be equals to the horizontal stress from 1 times the dimensions of the lower portions. So we have the 48.6 kilopascals times 4. Then we got the 194.449 as the area of this yellow rectangles, which is the P2 right here. This rectangles, the force from this yellow rectangles. Similarly, we do this pink area here now, this triangle representing the soil on the second layers to the lower portions of the wall. And since when we isolate it, we just look at a single layer of soils, then it's a triangle effect, because we just talk about the effect of the soil on the same level or the same layer. And the way we calculate sigma h2 here, as I previously mentioned, so this is your sigma h2, because we just consider the effect of the 4 meters when we calculate our sigma v2, the second part of it. So that's why, the base here of the base of this pink triangle have been taken care, which is 36.6, and times the height of 4 meter. Then this pink area, triangular area, give us the resultant force of P3. Again, P3 represent the lower portions of soil, the second layer of soil, to the lower portions of the retaining wall. So we know we successfully find out P1, P2, and P3. And the summations of those three will be equals to the total force. So the total resultant force from P1, P2, and P3. So we add up the three, P1, P2, and P3. The total force we got is 413.552, which is the resultant for P0 here we talk about. And now is the remaining task is try to find the locations of this P0, accounting for the bottom of these systems. So whenever we have something more complicated than just a triangles or simple area, when we have multiple areas of force come together, then we need to take moment at the base at this point. So if we take moment at point P, so we have the three force that come out from P1, P2, P3 pointing to the left, and then I create a counterclockwise stress. So P1, for examples, P1 is this force times the 4 meters to 1/3. So we know this is this dimensions is 1/3 of the 6 meter. So we have this dimension here as the moment arm for P1. So this is the P1 moment arm right there. Then P1 times this moment arm give us the first component, give us the clockwise loading, sorry, counterclockwise loading, and then P2 right here, which is here. So this is the moment arm of P2, and P2 is acting on the halfway or the middle of the mid height of this rectangle, because this is a rectangle. So the centroid is right at the midpoint. So P2 times half of the length of this rectangles, so PM times 2 meters, give us the moment of force come from P2. And similarly, we also do the same thing for P3. And P3, we just talk about this pink rectangle here. So we know, like, again, once we have only rectangles, the force act through the centroid, which is 1/3 of the height. So the moment arm equals to 1/3 times the height, which is 4 meters. And all this counterclockwise loading resist by the support from the wall. So now we have the clockwise loading, clockwise moments, P0 here loading with an unknown moment arm, which is Z that we solve for. So P0 times Z. So this way is the clockwise, and the bottom is clockwise, and the top here is counterclockwise. So balancing the moment calculations, then we can solve for Z right there, which is the C that we try to solve for, and we do all this math. So again, the P0 times Z give us the clockwise moment arms. The rest give us the counterclockwise moment arms, and we solve for Z. For this case is almost 3.292 here, which is the C. So I walk us through quickly and simply, just as a simple examples, how to solve for simplified problems in retaining wall design only with dry sand or dry granular soils at rest K0 conditions. So two very simple examples to start with. And please subscribe to my YouTube channels, and there will be more examples to come when we talk about 3-layer systems, and also talk about what if it is a saturated or partially saturated retaining wall design. So you could imagine the calculations will become a little bit more complicated when more layers to